Hey, hello guys, welcome to this video. Recently, I'm working on PBR, IBL, and GLTF model loading, and I have basically done these things. However, there is an optimization in the image-based lightning, which is IBL, called importance sampling, which is a little bit hard for me to understand. So we can see that the helmet has some artifacts under the strong light. But today we don't need to be worried about it because I'll talk about PBR first, which is the base of the IBL. As you can refer from its name, the rendering doesn't obey the real physics rule of light, but it more or less bases on the physics rule. So here are today's video's contents. We are going to talk about PBR's theory first, then I'm going to introduce why I give up the GLSL and use the HLSL instead. Finally, let's take a look at the code and run the sample app. First of all my contents today comes from the Learn OpenGL website. I'll just simply introduce the concepts. For more detailed theories, please refer to it. Besides, there is a reference section at the end of the page. There are lots of base theory there, or you can also check out SIGGRAPH courses. So for most real-time PBR algorithms, microfacet model is their base. The model basically says that a very tiny place on a model, which is about a pixel, consists of lots of small surfaces, aka microfacet. As you can imagine, if a small surface is rough, then overall the distribution of the normal of all these microfacets is relatively even. However, if a surface is smooth, then the normal of it, of all its microfacet would be same as the surface normal in general. The parameter that determines the distribution of the normal of the microfacet is called roughness, and the normal map, or the normal plus tangent data in model, is used to specify the larger surface normal. Then what will happen if a light is shot on a microfacet? As we learned from physics course, if a light shot on the surface of water, some part of light is reflected and the rest of the light is refracted. Therefore, the rendering model should consider both reflection and refraction. For the reflected light, it just gets out of the material. For the refracted light, it is absorbed by non-dielect material. However, for dielect material, refracted light can traverse in the material and get out from some places. If it gets out from the same side where the light gets in, the effect is called scattering. If it doesn't get out, it will be absorbed. It is also possible that it can get out from another side. In this situation, we can see that the material is transparent. Just like I said, metal always absorbs refracted light. Thus, we have another parameter in our shader, which is called metallic. If the metallic is 1, then the material is metal. If the number is 0, then it is a dielect material, and we need to consider the refraction. After this, we may ask a question. For a light shoot on a surface, How much is reflected and how much is refracted? In order to answer this question, we have to mention the Fresnel effect. From physics course, we know that the more the angle between the surface normal and the light, the more light is reflected. The water surface here is an example, so we can just use the Fresnel equation to get the percentage of reflected light. The rest of the light is refracted. Besides, the Fresnel effect exists on all materials. Great, now we have covered all physics theory under the hood. Let's take a look at how we can use the physics model to write down the rendering code. In order to get a result that looks okay, we only need to consider how much light is out from the light input side. It includes both reflected light and some refracted light, which can be described by the reflectance equation. In this equation, LO is the radiance out of a point, FR is called BRDF. It describes the ability of a material to reflect a light by giving light's input and output direction. For example, for a rough surface, the input light is scattered evenly to the surrounding area no matter the direction of the input light. However, for a smooth surface like a mirror, it only reflects the input light to the reflected direction. Under this situation, by giving the BRDF the two directions, the BRDF's value becomes 1. As for other combinations, the BRDF's value becomes 0. Li here is the input light's radiance, P is the point that we want to render, Wi is the direction of input light, Wo is one of the light output directions that we are interested in, N is the normal of the point, the dot product between the normal and Wi is to consider the light density decreases when the angle between light direction and the normal direction is large. And finally, the integral here means we want to consider all input light's energy contribution to an output direction. Now, if we connect the reflectance equation with the concepts mentioned before, roughness, metallic, Fresnel effect, we can find out that they are all described in the BRDF. For the modeling of BRDF, there are lots of options. Here I just directly use the model introduced in the Learn OpenGL, and the Learn OpenGL just uses the BRDF used in Unreal 4. In addition, Unreal 4 uses the Cook-Torrance BRDF model. So in this model, the diffuse part is just Lamberton. It means input light from all directions are just scattered out evenly when the light is out. For the reflected part, it includes 3 functions, function D, function IF, and the function G. The function D describes the distribution of microfacets normal, F is the Fresnel equation, G is the self-shadowing. The self-shadowing means if a surface is rough, the microfacets are likely to shadow each other, which can lead to darker surface. Let's take a look at the distribution function and the geometry function first. Unreal 4 uses GGX model for them. It basically means their equations are here, and please refer to the Learn OpenGL for more detailed derivation. Then let's take a look at the function f, which is the Fresnel equation. in rendering, we normally use the Fresnel-Sherlock equation to approximate it. The F0 here represents the reflected light when you shoot a white light along its normal. Different materials have different F0s, thus we only need to search the table for this value. If you looked at the table closely, you would find out that non-dielectric materials are gray and only metals have colors. Besides, the two equations here shown in the OpenGL is not strictly true. For example, the Ks before the F Cook torrents is just the F function in the second equation. So please remember that the Fresnel equation should only appear once in your code. Okay, now let's talk about how to use HLSL in Vulkan. Actually, it has been supported for a while. You can see that in the official Vulkan samples repo, all applications have both GLSL shaders and HLSL shaders. The Vulkan can use HLSL because Microsoft's DXC can translate HLSL to SPIR-V, and the Vulkan always reads in SPIR-V. This DXC doc is pretty good, and I recommend you to refer to this when you are writing the HLSL because there are some difference between HLSL and GLSL. In addition, Vulkan and the DX are also different, so the HLSL for Vulkan has some special syntax and concepts. So what should we do in order to use HLSL in our application? First, we need the DXC executable. You can find it in the Vulkan SDK. Then we need a HLSL script. Finally, we only need to execute the compile command by using the DXC. Now let's start from reading the HLSL shader code and see how I do all these things. Okay, so now let's take a look at our application. So, let's hit the run, and here is our application. It basically draws 14 spheres here. So the first line are spheres under the metal category. They have the metal material, and for the second line, they have non-dielectric materials. They're like porcelain and something like that, like plastic. So yeah, from left to right, their roughness increases, and yeah, so that's basically our test. So let's take a look at the shader of it. So, they are written under the 3-1 PBR basic HLSL, and yeah, let's take a look at the vertex shader first. Is quite straightforward. So for the VS stage, we output the position. This is the position before the perspective division. So it's the division after multiplies the model matrix, the wheel matrix, and the perspective matrix. The second one is the world position. Because we want every pixel's world positions. The third one is the normal. It's also in the world space, and for the parameters here, it is the first element is metallic, and the second parameter is the roughness. So yeah, it's non-interpolation because we don't want the rasterizer to interpolate all these values. So yeah, the second struct is the input. So we use the vertex buffer to feed information into the vertex shader. So the first one is the position, which is in the model space. The second one is the normal. I think is also in the model space. And we also need a UBO, and this is the view matrix multiplies the perspective matrix. And yeah, here we just write all spheres world positions into the vertex shader, so we can use some sort of hack to just get their values by using index instead of feed their value by using the UBO here. So yeah, the UBO is attached to the B0 register, and we have a function here. It is used to transform a position like 15, 2.5, -8 to the model matrix. And yeah, here is our main function. So yeah, here's our trick. So we basically use the instance draw. So when you use a Vulkan command to draw, you may notice that it has a field which is called instance. So it basically means for each instance, the hardware would give the vertex shader a special ID. So here's the instance ID. So from the array here, you can see that we have 14 IDs for 14 instances, which corresponds to the 14 spheres that we saw. Yeah, so then it is the vertex input. It is just the vertex buffer, and yeah, we get the model matrix, we get the roughness, and we yeah, so we mode 7 to the instance ID to get the first line and the second line, so we can make their roughness 0 when they are at the first column, and then increasing their roughness when the number of columns is increasing. So yeah, they are pretty straightforward. We multiply the model matrix to the position and get the world position. We multiply normal and get the world normal. So yes, we feed them into the output, and the output just output. Okay, so yeah, let's take a look at the fragment shader. So the first thing you see is the ggx model.HLSL is the biggest reason why I use HLSL, because I don't need to write my own include logics in the code. I think, or I believe, GLSL doesn't support it by default. So yeah, actually it's a file under the shared folder. So for the third level examples, so you can see that we have already got 3 third level examples. We will use the shared library because the scale of examples is too large, so we have to reuse some code in order to get some readability. Yeah, so this is the file. It has all kinds of GGX models functions that can be reused, and yeah, we will go back to it after we read them here. So yeah, as we can see, the 3 input parameters here was given by the rasterizer, and they were from the last 3 parameters or elements in the VS output struct. So yeah, this one is the light color, is the light radiance actually, and we give the gold color to the reflection albedo and the diffuse albedo. And yeah, we need the camera position because we want to get our WO, which is the light output direction. And yeah, we normalize the pixel world normal in order to get the real normal vector. And yeah, this cosine theta is used to account for the light density decrease when the light shoot to a surface horizontally. So yeah, then we get metallic roughness, and we try to calculate LO here. As we know, we only have 4 lights in the scene, so the 4 here corresponds to 4 lights, and yeah, it means we only have the our Li only has this 4 places, and our BRDF is only 1, or only has value when the Li is from this 4 directions. So yeah, that's why we only need a loop with 4 times, or 4 times loop. Yeah, so we get the light position here, and we get the light input direction. We have the normal direction with the H. This is the vector between the Wi and Wo. You can think it as a normal. Yeah, so here's the distance is used to decrease the intensity of the light. So it's some sort of attenuation, and yeah, so they are basically it. We use the distribution GGX to get the NDF, the normal distribution function, and this is our geometry function. So if you take a look at the Learn OpenGL, you may figure out that the direct lights geometry function is different from the image-based lightning geometry function. So I separate them out, and then we get F0. This is for the materials like plastic, so their reflection color is basically gray, so we just give them 0.04 here, and yeah, we lerp them, or in GLSL I think it's just mix, and we use the Freesdale-Sherlock approximation to get the final reflection. And yeah, so we multiply N, F, and G together to get the NFG that we saw for the Cook-Torrance model. And yeah, in the model we also need a denominator. And yeah, so after the real normal cosine theta is used in the denominator, but the light normal cosine theta is used for the light density problem. And yeah, so they are here. So KD is the diffuse percentage of the light. It can just be derived from the reflection part with it, which is just the value of F. And yeah, we add it to LO, and finally we get a color here. Yeah, and we also have the gamma correction because the value in the hardware is not the real value that is given to the pixels on our hardware screen, because our human eyes has some special are more sensitive to light that is darker. So yeah, so in order to make the interval of the values becomes similar to the feeling of human beings, the hardware do some remapping. However, we hope that our color calculated here is the real color, or the real intensity on the pixel or on your screen. So we just map it to, encode it so it can be decoded by the hardware. And yeah, that's basically our shaders. Then let's take a look at our applications CMake file. So yeah, here is quite straightforward. We just create the application target. So from this line, we are trying to compile the HLSL code in our project, which is the important part. So yeah, I'm going to explain it in details. Here is the repo of the shared library. So under this folder, you can also find a HLSL compile Python script. It is used to compile the Sapphire Vert HLSL and the Sapphire Fragment HLSL here. So it's really important. And before it, we have a dummy file. The dummy file is created by specifying that it has the symbolic property. So we want this dummy file and the shader compile target or custom target, because we hope that our normal or the PBR basic application depends on the Python scripts here. So whenever you build your project, these compilation Python scripts were triggered before the application build. So you always have your updated SPIR-V compiled from your HLSL code. So yeah, after this, let's take a look at the Python scripts. You can find this Python scripts under the shared library HLSL here. And let's look at this code. So yeah, src specifies the target HLSL shader destined direction or directory, specifies the output folder. So the dx command string here just help you to find your DXC on your system, and the profile here is just the version of the HLSL, and yeah, the entry point is main, and we also want to include the HLSL, the shared library HLSL folder, and into the searching path. So you can include something like ggx model.hlsl in your fragment shader, just like this. So after this, we have some extensions. So I'll make some ray tracing examples, but now we don't have them. For multi-wheel, we need it for cube maps, and others are also needed normally. So yeah, this is the Python script that is used to compile that uses the DXC to compile the HLSL shaders. Okay, so finally, let's take a look at our C++ code for the project. So this is the first sample at the third level. So for the third level samples, I decided to add some abstractions. So as you can see, it is a little bit more complicated. And here's our application class. It inherits the GLFW application. This application basically means all its child applications should have a GLFW window as well as a swap chain. And let's take a look into this GLFW applications. By the way, they are all in the shared library, and yeah, it inherits from application. Application is more pure, so you can, it only has Vulkan devices, instances, and the command pool, and some basic things, so you can build an application without any swap chain or without a window. For example, my cube map tools and image-based lightning tools, by the way, generation tools, inherits this application class because they don't need a window. Yeah, so let's come back to this application. So yeah, here, so most code are written here. I recommend you to read the code because our video is a little bit long now, and it basically just do initializations or what, and we use command buffers or we record commands into its command buffers in the main function. So you can find the most logics here in the main function. So yeah, we create the application, we initialize it to create its pipelines, and we get into the main loop, and we start the frame, get the image from the swap chain, and we try to record rendering commands. And I think the most important thing that I want to mention here is the Vulkan command draw. Let's take a look. Yeah, because it has the instance count that I said before. So each instance has a special instance ID, and all the vertices under this instance share the same instance ID. So you can use this to differentiate a vertex from different instances. And yeah, we have 14 spheres. So here the instance count is 14. And yeah, all other things are quite straightforward. We just render it to a render target, to a color target, and then give the render target is a swap chain image. So we just present the image, and boom, we get the final rendering result. Yep, so that's it for our video today. So if you like my video, please remember to subscribe my channel, and I will see you in my next video. Thank you very much.